Good morning, GM. Thank you, everybody here, for choosing to spend your time at our third inaugural NoirCon.
Hello. Thank you for being here. So I'm going to present, trying to give you hints on how to write efficient Noir code. But first, let me explain the title, because you should not write circuit. I did that because when we were developing Noir, our motto was write code, not circuit. And so that like anybody can generate zero knowledge proof, and you don't need to be a cryptographer. You just need to know how to program. So that was the idea, but knowing, so what do I mean by circuits? So like circuit is the output of the compilation of a Noir program. So Noir is writing the circuit for you. You don't have to care about that, but it's important to know what it is doing so that you can write efficient Noir code. So we need to know what is the circuit, basically. Okay. The good news is that a circuit is a very simple thing. Sorry? Okay. So it's just a set of equations, like living in a prime field. And this equation describes the computation that you want to prove. So it's just literally a bunch of equations. So it's very simple, in fact. In the context of Noir, we have also more in the output of the compilation, what we call gadget, or what in the context of Noir we call black box functions, which are stuff that is implemented. It represents a small computation that is implemented by the proving system, and it's implemented like much more efficiently if you wanted, rather than doing it like using a generic circuit. So these black box functions, usually they are done using lookup tables. So lookup tables are a very important primitive of cryptographic primitive. And this is how you can access to this kind of primitive using Noir. We will see some example of that later on. Okay. So this is a very simple example. When I want to multiply a matrix by a vector, a 3 times 3 matrix. So like the multiplication, matrix vector multiplication is very simple. So like you say, okay, this is an equation. I can do the same for the second coordinate and so on. So I already have my circuit. Well, not exactly. The trick is that in your equation, you need to have only one multiplication. So we call this equation with only one multiplication, we call it a gate. And so how do you come from this to this? You need to create intermediate variable for each multiplication, then you can sum the result. Okay, so what we learned here that a multiplication costs one gate. Okay. So yeah, if you want, you can try the example. It's very easy to install Noir. I put some QR code, but you cannot install it on your phone. So just because it's nicer with the QR code, but no, you really need to follow the link, and it's very easy to set up if you are using Linux or a Mac. If not, then I don't know. It would not be easy. So this is for Noir, but you need also our proving system, which is Bartenberg. We call it BB. But installing it is also very easy. Okay. So this is a matrix multiplication example. So if you are not familiar with Noir, you see that it's very straightforward to code with Noir. So it's a Rust-like language. And here I added a command line that we will be using. It shows you the circuit size, so the result of the compilation, the number of gates that you have. So it also tells you the number of ASCII codes, which is an intermediate compilation step. But what really matters is the circuit size at the end, so 66 here in that case. And you can see that also we have just 3 coefficients, so the number of opcodes is only 3. But in reality, because of this, like 1 multiplication per gate and so on, we have more. I don't know why it is 66, frankly. It should be like less than 30. But I didn't investigate. I think 66 is a good number. Okay. So we have seen what we can do with a circuit. Now, what cannot you do with a circuit? Well, you cannot do integer arithmetic. Like if you want, for instance, to compute the average of 2 numbers, you say, oh, good, I've got my equation. I don't need Noir, I can just use this in my circuit. Well, no. This computation is not the average of the x and y. And the reason is because 1/2 is not 0.5, it's a big integer number. We are in a prime field, remember, okay? Another thing that is not easy to do is a comparison, because it's not an arithmetic operation. So, like, everything that you cannot do in a circuit, you need to emulate it, and this is very costly. So, fortunately, for comparison, we can use black box functions, which call it the run check. It's a very, very well-known cryptographic primitive. So run checks allows you to assert the bit size of a number. So in case of comparison, you would need like to do 2 run checks and a few arithmetic operations. So what you need to remember is that a run check costs between 1 and 10 gates, depending on the bit size. Okay, a circuit also doesn't have any memory, because it's only like numbers in an equation. So also this needs to be emulated, and this is horribly costly. But we have also a dedicated black box for that. So and yes, you don't really need to worry about the black box, because like Noir will lay down the correct black box for you. But what you have to remember is that memory operations are costly, even with the black box. So if you want to do a read, it will be 2 gates, more or less, and a write would be like, in average, 4.5 gates. Hello. Okay. So why do I say dynamic read and dynamic write? It's because, like, if you want to access your memory at a constant index, an index as you know, like 5, 8, whatever, usually it can be optimized out. And one more thing, we need to pay for some initialization costs, which correspond to the array size. So even if you have only one dynamic read, it will be 2 gates plus number of elements in your array. And also these numbers are only for arrays of simple type, like numbers. But if you start to use composite type, it will not be the same number, so would suggest that you want to avoid that. And of course, what you don't have in a circuit is control flow statement, like using if, loops, break, continue, function calls. Okay, so all this needs to be emulated, and then it will be costly. Okay. So what we have learned here is that writing circuit is difficult and error prone, and circuits are not really efficient. So like one of the reasons also is that this integer arithmetic versus prime field. So when you want to do like normal computation with integers, it needs to get emulated by the field. But then you need to remember that you are executing this on your computer, which is like a binary computer, like using bits. For instance, like register of 64 bits. But our fields are much, much bigger, like around 256 bits. So then this will need to be emulated again by a binary computer. So you have to do this kind of double emulation that is at the end very slow. Okay? Okay, but the problem is that in a stack we want to use Noir for private smart contract. That means contract like programs that run on your device because you don't want to give your data to anybody else. So you just want to generate a proof and then say, okay, my transaction is correct, you can check the proof. So it must run on a personal device like a phone, so it must be efficient. So we need you to write efficient Noir code. And how to do that, given that Noir is creating circuits that are slow? Well, the answer, in fact, is quite simple. If using a circuit is slow, let's not use a circuit. And for this, we have this concept of unconstrained functions in Noir. So I say it's a unique feature, but like, it's not unique. Like it existed well before Noir, so like it's not unique at all. But I think that the implementation we did in Noir is very good, like very well integrated. It's very easy to use, and yeah, you just add unconstrained keyword in front of your function, and that's it. So what can you do with this unconstrained function? So an unconstrained function is saying to Noir that, okay, this computation, do not put it in a circuit, put it outside the circuit. So that means that the cost is 0, like in terms of number of gates. Okay? Then what you need to do, of course, is to validate the result that you get that is computed offline, like outside the circuit, I mean. You need to validate this in a circuit, of course. So you still need Noir. Okay, so we'll see a very simple example, like the classical one, like how to do a division. So if you want to compute a division inside the circuit, how you would do? Like a division we are in a prime field, remember? So division, you need to multiply x by its inverse, the inverse of y. And the inverse, you can get it using the Fermat's little theorem very easily. So here P is a prime number of the prime field, like the characteristic of the field. So it's a very big number, like more than 250 bits. But fortunately, this can be computed efficiently using the famous square and multiply algorithm. But still, it requires log P multiplication. So to compute this, you will need at least 250 multiplications for just one single division. So it's kind of costly anyway. So can we do better? So yes, of course, with unconstrained functions, which is kind of straightforward, but maybe not. So yeah. This is something I'm trying to explain to my daughter for so many times, and she still doesn't get it. But yeah, if you move the y to the other side, then you have a multiplication. Come on. Okay, so how can you do it in Noir? So yeah, you don't need to do it in Noir because Noir is doing it for you, but still, if you want to, you can still do that. So you can use an unconstrained function. You should just say that it's unconstrained. I call it divide, and then this is doing the real computation. And then we just check in your circuit. So main is is the circuit that you are going to compile. To use the unconstrained function, you need to specify that with this unsafe keyword that tells you that the result of this function is not proven, so it can be anything. Okay, no problem, because I will assert that this relation is true. So this is happening in a circuit. And when you use an unconstrained function, you must be very careful because you need to think about all the edge cases. In that case, the edge case is when y is 0 because you are not able to divide by 0. So, okay, no problem. I just assert that y is different than 0, and that's it. So this costs one multiplication. This is another multiplication as well. So and maybe another one to return another gate to return the result. So like it costs 3 gates, and that's it, instead of 250 multiplications. Okay, so quite nice, no? So now I'm just going to give you, trying to give you some intuition on how to do that with more example, and that's it. So another example, which is also simple, is what if I want a function that finds an element inside an array that is sorted, okay? So like the simplest solution will be to do a linear scan. And when I get to my elements, I just return it, okay? So, and that doesn't work. And the reason is here we are doing a early return, which is a control flow statement that doesn't work in a circuit and that we do not emulate, because if we would do it, it would add a cost, and it will be like a kind of invisible cost. So we don't want that. We want you to be aware that, okay, this is not possible. How to do it differently? So one way to do it differently is to go over the whole array and then just check when we reach our elements, store the result, and then return the result. So, but that means that there is no, like even if my element is the first one, you will process the whole loop. So this is an important point when you use an algorithm in a circuit, in Noir. You must remember that the cost will always be the worst cost of your algorithm. Okay. We know that we can do better. And the classical way to find an element in an array is to use binary search, which will be a log n cost. But if you try to do that, what will happen? Like, because here we have recursive function calls, this doesn't work in Noir as well. So function calls are emulated. That means that they are inline into your circuit. And if you call yourself, then of course it doesn't work well. Okay, so that's not a very big problem because you can always write an iterative version of a recursive function. But even if you do so, here the benefit of the binary search is that you have your array, you split it into two, and then you only search in the relevant part. But remember that if is a control flow, so it's emulated, and how do we emulate it is by you need to process the two branches. If you process only one branch, then it will not be zero knowledge because you will know in your circuit, oh, we are only executing this branch. So we need to execute the two branches. That means the gain that you do by this trick is completely cancelled because you need to process the two. So like this binary search will be linear time, it will not be log n. And because of all this overhead, it will be worse than the previous linear scan. Okay, still can we do better? Yes, with unconstrained functions. So here the idea is to do, okay, no problem, I will do my binary search outside the circuit using an unconstrained function. And then I just assert that the result is okay. So I assert it here. I hope you can read it. I'm not sure you can read. Yeah, more or less. Okay, so I just assert that the index given by the unconstrained function correspond to the element I was searching for. But here again, we need to pay attention to the edge cases. So this is fine when X belongs to the array, but what if it doesn't belong to the array? So yeah, in that case, we need to handle this case as well, else it will not be safe. So this is what I do. This is why I need all this. So like basically, either X is outside completely the array, so I check this, or it's inside, and then if it is inside, it must be between two elements of the array in terms of the range. Okay? So this is what I do here. But it still like doesn't change. There is no loop here at all, so I just do 1, 2, 3, 4 assertions, some comparison, and that's it. So it should be like a constant cost, right? but it's not what I wrote here. So do you know why it is not constant cost? Why is it a linear cost? So remember what I told you. Here we are using an array. We are reading at a dynamic index into the array. So that means we have to pay for the initialization cost, which is n in that case. But still, this is better than the linear scan, because in the linear scan case, like for every step, we do all this, which is a comparison and a if. So this will cost at least 3 gates per step. So the cost will be like O of 3n, something like that. Whether here, the initialization of the array is exactly n, and then we have a constant overhead. So it's better. All right. So now we know how to find an element in a sorted array, but my next question is, how do we sort an array? So you may remember this interview with Obama. So what is the most efficient way to sort an array of with lot of numbers? And yeah, you should not use bubble sort, because bubble sort is quadratic. The good point about bubble sort is that it is very simple. So for instance, if I try to do a selection sort, which is also quadratic, here the cost will be bigger. We will see this, maybe I can, where can we find it? I don't know. Shit. Okay, we'll see later. So what I wanted to show you, I don't want to break the setup, like is running the Noir profiler with this, and the previous one, and then you can see the number of gates and what type of gates there are. And in the previous one, here, you don't have any dynamic memory operation. So all the array access are optimized. And the cost is, I think it's 50,000 gates for 100 array, an array of 100 elements that you want to sort. And here the cost is 3 times more, and because of, like here you are doing dynamic access on your array. Okay. So again, we can say, okay, but we can do better. We can use n log n sorts. So here I took the example of merge sort. Merge sort is very is very simple. So you divide your array in two. You recursively sort each part, and then you can merge the two because they are sorted in linear time. Recursion doesn't work well, as we know, so we will need to get to an iterative algorithm, and then it will not fit on screen. So I just brought here the linear merge, so like the first layer. So we will need to do log n of these operations. And still you can see, oh, there is a lot of if, there is array access and so on. So here, like a good idea would be, okay, to see what do you get with the Noir profiler. And what you would get here is, I think the cost is around 10,000 gates, but just for one layer. So doesn't compare well to even the bubble sort. Okay. So obviously the correct way to do sorting is to use unconstrained functions. So let's see. So the idea is that you sort your array outside the circuit, and then you check that the result is correct. Now, how do you check that the result is correct? Well, one part is easy, is to check that the result is sorted. This is very easy. And we can see that this is linear. I just go over all my elements and check that one is bigger than the next one, the previous one, sorry. All right, but that's just half of the story. We still need to know that the elements in your result correspond to your initial array. And what does that mean? That means that your initial array and the new one, the sorted one, must have the same elements. So that the elements may have been permuted, but they are the same. They come from the same set, okay? So this is a kind of permutation check that we need to do. So how to do that? So for this, I'm using this unconstrained function that gives me what I call the sorted indices. So what I mean by that is that if my smallest element is index 3, for instance, then this array will start by 3. If the second smallest one is index 8, then the second element here will be 8, and so on, okay? But this is totally unsafe for now. So what I need to do here, I check that every element of these sorted indices correspond to 1, 0, 1, 2, up to n minus 1. So here, using another unconstrained function, I prove that this array contains all elements between 0 and n minus 1. And since its size is n, then it must it is exactly this, okay? So, sorry. So what I have proven here is that this array is a permutation of elements from 0 until n minus 1, and that's it. Okay, now I need to compute in circuit the result using these sorted indices, which I do here. Okay, and this proves that my result, the element of my result correspond to the initial array. All right, and then the final step, that as we already saw it, is to check that it is properly sorted. Okay, so now you can see that we have 3 loops over over 0, n, and like inside we just do a small assert, just 3 asserts. So the cost here is linear. So we are even better than quicksort, merge sort, or whatever, which is kind of cool, no? I think. Okay, of course. There is no magic, there is no free lunch. Like even at Devconnect, you have to pay for your lunch now. So you need to sort at some point your array really. And this is done inside this function, get sorting index. So how does that work in the stack? So you have your program, you compile it with Noir, which gives you the circuit. And it will also give you the kind of assembly code of all your unconstrained functions that you are using. And then you need to execute to get your witness assignment. You need to execute your program. And at that time, Noir will run your unconstrained function. So it will sort the array at this time using the code that you provide. So you need to, like here, do not use bubble sort because the execution will be very slow. It will be quadratic again. So you need to use efficient sorting here. Okay, so you need also to pay attention to that. Even if it is outside the circuit, it has some impact during execution time. Okay. Yeah, so this is this graph was done using the result of the Noir profiler that I didn't show you. So you can see that This is a logarithmic scale, so like bubble sort, of course, is very, very big. And this is not a much short, but only the first layer, so in reality, it's more than that. And this is what I wanted to show you, but here, like, we don't see much. So believe me, with the bubble sort, we only have run checks and arithmetic operations. So it's very simple and costs 50,000 gates. For the merge, if you look in detail, you will see that we are using a dynamic memory operation, we are doing run checks, we are doing arithmetic operations, so it's very complex. And the cost here is 10,000 more or less, but just for the first layer. And with this unconstrained version, the cost is 700 gates, so much better. And we have a lot of memory operations, a few arithmetic operations, and we should have run checks as well. Okay, here we have run checks. Okay, so it's always a good idea to check with the profiler what you are getting, try different alternatives, see which one is better. Okay, so in conclusion, what have we learned here in this workshop? So if you have to remember one thing, is when you want to write a Noir program, then you use Noir to write a circuit that validates a result that has been computed in an unconstrained function. This is what you try to do. It doesn't always work. I mean, it always works, but it is not always the most efficient thing, but usually it's very efficient. You need to check and validate with the profiler. So in more details, we have learned that circuits are inefficient, yes. Multiplications cost 1, addition are cheap. Noir black box, they are good. They are lookup tables. With the profiler, you should focus on the circuit size, the number of gates. When you have an algorithm in a circuit, it will be the worst cost that you need to take into account. Dynamic memory comparison are costly. And for memory operation, do not forget the array initialization cost. If is not what you think it is, so use it with caution. Keep it simple and smart. So smart, I mean like you need to validate all the cases, all the edge cases when you use unconstrained functions. And also, last one, when you are using unconstrained functions, you should also try to optimize them, but this time using like normal programming language strategies, like normal stuff. You can use early return, use them. You can use if without problem, it will be good, and so on. Okay, that's it. Thank you. So if you have any question.
Yeah, about the unconstrained space, what is the language actually executed? What is available for you? It's not Rust, it's still Noir, but compiled to native bytecode. What are the features of the language in this specific context?
Yes, so it is still Noir, but it's Noir with more feature. Like you can, as I said, for instance, you can use an early return. If you use early return syntax in a Noir program, not in an unconstrained function, it will give you an error. If you use it in an unconstrained function, you will be happy. So it is Noir, but with more features. This program, yes, but it will be a Noir lib, but you can import. And then it's part of, it will be part of your library as well. So like it's fully native in Noir, in fact. Like that's why I was saying that it is very well integrated. This concept of a unconstrained function in Noir, I think it's well done. So it's completely transparent. You continue to write Noir. And in terms of like more technical detail, so after, so you write it, and then it gets compiled to some assembly level code, which is like only our own assembly. And the reason is because in Aztec, we have private execution, but we also have public execution. And then for public execution, we need to run in a VM. Just to, in case of something goes wrong, we need to prove that the result is failing, rather than having a proof that you cannot, that does not verify. So that's why we need a VM. And so to have a VM, we need to have some bytecode. And this bytecode is the same as the one that we have for unconstrained functions. So it's our own bytecode, let's say.
Thank you. It is very interesting. I had a question about, you mentioned with the division example that is actually already optimized in Noir. Is there a way for us to know when it is already optimized by compiling it?
Not really. Like the basic stuff, you can expect it to be optimized, basically. More complex stuff, probably not.
Okay.
And then you can check on the profiler, if with the profiler, if it looks good or not.
Thank you. I wanted to ask, from someone that has some but little knowledge of Noir, you showed some examples of very complex functions that you've used it unconstrained followed by asserts. So is it a good way of using that to run away from very complex and costly functions, or is it not?
So yes, so that was the point of my presentation. So it will not remove the complexity. The complexity will still be inside the unconstrained functions. So you need to write this code. It's just that this complexity will not run inside the circuit, because we have seen that inside the circuit it's much slower. So that's the idea. Like you move the complexity outside the circuit, and you just check that the result is okay using these asserts. Yes.
I had another question about the unconstrained part. Is there any privacy concerns because you're outside of the circuit?
No concern at all, because it's done by the prover. So like there is no problem. It's done by the prover. When you execute your program, you are still the prover that is doing that, and this will generate all the witness, which means the result of your unconstrained functions will become a new witness, but a private witness, not a public witness. So it's fine. And then these witnesses will be used to generate the proof, and in your proof you don't have them anymore. You don't leak any data. There is no privacy problem at all.
The only problem should be forgetting about the asserts. That is the only concern that may happen, may go wrong. Like that you do the unconstrained function, but you don't verify that it's computed. That it will be the only. Sorry, that will be the only possible issue from the side of the developer. Like that you execute the unconstrained function, but you don't do the assert that the computation is valid.
Okay, yeah. If you miss some asserts, then it's a problem, but not from your privacy. It's a problem for the verifier. Maybe So the verifier is not verifying the correct thing.
So the unconstrained execution environment is optimization, and it happens at runtime. I think in other ZK systems, the paradigm was more like to execute everything entirely beforehand and put the result or the pieces you want as public or private input of the circuit you are building. It's kind of a different but similar purpose way of doing things. Is it still useful, like this way of having another implementation of your program and compute it beforehand in like regular Rust environment or Python environment, and then like give the interesting part as public input?
Yeah, so it's similar concept. It's the same. The benefit of doing like using a Rust, for instance, program, it will be speed. It will be faster than executing it in our assembly code, our own assembly code, because then it's another layer. Like we need to execute it, to read the code, to execute, etc. It's not like it will not be native compilation of the unconstrained functions. So it's a kind of a VM that we use for that. So the only difference will be speed, but then it's much more easier to use and it's well integrated into Noir. So sure, I guess. Yeah, we need to see with the organizers. But yeah. Okay. Thank you then.